Okay, in this video I'm going to discuss how to find the molecular formula, assuming that you have the percent composition of a compound. What some people would do here is they would find the empirical formula, then assuming that they were going to find the molecular formula, they have to know the molar mass, and then divide the molar mass by the molar mass of the empirical formula, and that gives you an idea of what it had been reduced by. I can show you what I mean by that using an example here. So we can do that, but I'm going to show you after that actually a simpler way to do this. So this is the way that would be described in the textbook, and this is probably the most common way people will do this, but there's a little trick that's going to make this a little easier. So step number one, find the empirical formula. Just like we did yesterday, we'll assume 100 grams. And now we can convert these percentages into grams. So for carbon, that means we have 40 grams. Hydrogen, we have 6.7 grams. And oxygen, we have 53.3 grams. Now, we're going to divide by the molar mass of each element, and this is going to get us a number in terms of the moles. So carbon's molar mass is 12, hydrogen's is 1, and oxygen's is 16. So 40 divided by 12 is 3.3333. This is going to be 6.7, and 53.3 divided by 16 gets me 3.333. This again gives me a ratio of the actual number of moles or particles in this substance. So that's good. The only problem here is it's not a whole number ratio, so we're going to divide by the smallest one. After this, remember, we would look for the decimal place to see if we have to multiply back by something, but hopefully we won't. We won't in this case. 1, 2, 1. So the empirical formula of this compound is C1H2O1. Now, let's get into what it says here. Find the molar mass of the empirical formula. So the molar mass for this, C1H2O1, is 12 plus 2 times 1 plus 16, right? The molar mass of the individual atoms that make it up. 14, so that's 30 grams per mole. Now we're going to divide the molar mass of the actual molecule. In this case, it's given by 180. So the molar mass of the actual molecule divided by the molar mass of C1H2O1. So 180 grams per mole divided by 30 grams per mole. That gives us a factor of 6. What that means then is my empirical formula is 6 times smaller than the actual molecule that I expected to find. How did we get a molecule that was 6 times smaller than what we expected to find? Well, these guys must have been reduced by a factor of 6 when we went from the molecular formula to the empirical formula. So what we can do is take that 6 and put it back into the whole molecule. And then we get the correct molecular formula. So we found the empirical formula as shown in the last video. We found its molecular mass. We divided the molecule by the molecular mass of the empirical formula, and we saw that the molecule was 6 times bigger. So what that must mean is if this is the lowest whole number ratio, and the actual molecule I want is 6 times that size, I should multiply each one of these things by 6 in order to get the original molecule. So that's probably the common way to approach this, and that certainly works, but I'm going to show you a little trick that I think is clever and make it a little easier. Just going to erase everything we've done here. Okay, the trick is this. What if instead of assuming 100 grams, we assume the actual molar mass? It's going to make turning these percentages into masses a little more difficult, but the big advantage to it is when I get the answer, it's going to spit out the actual molecular formula right away because I've assumed that I have 1 mole of the substance instead. So let's see how to do this here. Oh, a little more racy here. There we go. So for the carbon now, if I had 180 grams and I have 40% of the compound is carbon, that means 40% of the 180 grams, and remember of in math means time, so this really means 0.4 times 180 grams. So if I had 180 grams total, that would mean that 72 of my grams were carbon. For hydrogen, I have 6.7% of my total 180 grams is hydrogen. So doing that multiplication, remember whenever you use percent in a calculation, it needs to be in its decimal form. Getting me 12 grams of hydrogen. And then, need a little more rice over here. Some more stuff here, make sure I have lots of room. There we go. Sorry. And then for my oxygen, I have, what was it? 53.3%? 53.3% of my 180 grams. So that works out to be 0.533. Oh, what did I do there? I'm on this one. There we go. 53 times 180, 96 grams. Done a little rounding here, but it's just going to make my life easier. Now, just like I would have with the empirical formula, I'm going to divide by moles, or I'm going to divide by molar mass to get moles. So remember, N equals M over big M. So here I'll divide by 12 grams per mole. Here, 1 gram per mole. And here, 16 grams per mole. So 72 divided by 12, that's 6. 12 divided by 1 is obviously 12. And 96 divided by 16 is 6. And see, what happened here is because I knew how big 1 mole of the molecule was, if I assume that, then the corresponding masses will be the real masses for 1 mole of the molecule. And then when I divide them out to get them all into moles, I get the number of each kind of atom in 1 mole of the substance. And so it spits out the molecular mass right away in one step. So it's a little annoying to find all of these masses, but if I know this, then I get a much simpler whole number ratio when I go to do the problem in the first place. And to me, that's worth it. Okay, so this is just me putting that into words. So a trick to make it a little easier, don't assume 100 grams. Instead, assume the mass of the sample is the molar mass. That way you get the number of moles of each atom that there will be in 1 mole of the molecule. So here we go again. 202 grams per mole is the molecular mass. It's comprised of 47.5% carbon, 4.95% hydrogen, and 47.5% oxygen. So I'm going to assume 202 grams. So that means for carbon, hydrogen, and oxygen, I'm going to go 47.5% of 202 grams is 0.475 times 202 grams, which works out to be 96 grams. Maybe you would rather see this from the actual formula. Percent comp of hydrogen, or the percent hydrogen, is equal to the mass of hydrogen divided by the mass total. So with that in mind, the percent hydrogen given for this sample is 4.95%. That would be the mass of the hydrogen divided by the mass of the total. Sorry about the updates, just ignore them please. So 0.0495 mass of the hydrogen divided by the 202. So that would get me a mass of hydrogen, which is 10 grams. So that's just going through, and in the end, if you looked, what I ended up doing here was just multiplying my percent by my mass anyways, times 202, times 202. But that just shows you one more time, using the formula, why it ended up being percent times the total mass. But if you want to think of 47.5% of 202, whatever's easier for you to keep track of. Now I have 47.5% of 202 grams, and that's going to work out to be 96. So if I assume 202 grams, I get 96 grams of this, 96 grams of this, and 10 grams of that. Now, converting to moles. (96 divided by 12), 10 divided by 1, and 96 divided by 16, because the molar mass of oxygen is 16, carbon is 12, hydrogen is 1. And so I get 8 to 10 to, I think this is going to be 6, yep, 6. So this compound is C8H10O6. And that, because I've assumed the right molecular mass from in the first place, is the right molecular formula for the compound right away. So again, you can do it this old way, which is the way the textbook will show you how to do it, or you can use this little trick that actually a student showed me a number of years ago.